where we ended was looking at our electron configurations and how they played out. So what we want to do here is drill in a little bit more on our electron orbitals. So we'll real quickly kind of review the basics behind it. So our first basic, we have energy levels. These energy levels start at 1, 2, 3, 4, 5, 6, 7. And what we referenced was that the energy level is actually labeled on the left-hand side of our periodic table. Hand side, periodic table. So if we look, there's usually a number sequence there, and it is numbered 1 through 7. Each of those energy levels divides out into an orbital type. Right? That type of orbital starts with S. When we move up in energy, we gain a new type of orbital, which then moves to our P. We move up in energy, S, we repeat our P, and we move then to D, and we continue this so on and so forth. After each type, we end up with orientations. Some types have multiple orientations. The S orbital, there's only one orientation, so there's only one orbital. But the P, as we're showing, has 3 total orientations. The D has 5 orientations. That information is embedded in the periodic table. So I do want you to remember that information. So S had 1 orientation, P had 3, D had 5, and then F I'm going to leave as kind of a question mark because we'll see that when we look at the periodic table, and we'll try and find where those numbers are coming from. Each of those orbitals can hold 2 electrons, so the S gets us a total of 2, 6, 10, and then we'll deal with the F in a little bit. So those are all the electrons that can go in, and the electrons we can put 2 in because of spins, right? And so what we've got now is a way to kind of represent our orbital diagram, or sorry, our orbitals. And it's a way to label where every single electron is for an individual atom. So we're for all of the electrons for an individual atom. And so that's kind of neat. One of the things that you'll be asked to do is come up with electron configurations, which is to identify the location for every single electron on an individual atom. And that becomes a little bit more tedious, but at least at the lower level chemistries, there are kind of pseudo cheats to get through it because you don't have to nuance every single little detail. You're looking for the big picture stuff. One last thing I want to kind of draw your attention to that's going to become important is that if we look at those energy levels, you'll notice that the gaps between them aren't all the same, okay? So if we look here, the gap between 1 and 2 is a fairly large gap. When we look at 2 and 3, it's getting smaller and smaller and smaller, okay? And at the end, okay, it's minuscule. Okay, what does that due to? Well, that's due to the kind of the wave function of those. One way you could kind of consider it is that we're looking at trying to share an equal volume around the individual atom. The further away you get, there's a larger sphere, if you will, which means it has to get further away to get access-ish, okay? But it is important to recognize that the energy levels are not equally dispersed, that there's this kind of increasing stacking, if you will, the higher up in energy you get. Okay, and that's going to become really important because if we say throw on that 4th energy level, the thing that we need to note is that the higher up in energy we get, note that energy versus that energy almost identical. And so we'll end up getting weird fill patterns when we get high enough into the periodic table, or low enough in the periodic table, high enough energy, where the electron configurations make less and less sense. And this is where knowing a fill pattern can help out. It's also very helpful to actually know your periodic table and interpret it, because that's how you can pull some information out. Right? So I did say we'd look at some electron configurations. So let's go ahead and pick an example. Let's say I want to find where there are 7 electrons. I want to identify 7 electrons. In this fill diagram, I could go through and say, well, 1, 2, 3, 4. We fill lowest first. 5, where's the next electron go? Right? Because there's really two options. I could put it right next to it, okay? Or I could put it in one of the other orbitals, okay? Because those are all roughly the same energy. One of the patterns that we've discovered by studying electron fill rates is that we'll go lowest energy first, and we'll pair before we go to a higher energy. So in this case, I've labeled out 5 electrons. That was the 5th one. The 6th one is going to go into one of the unoccupied p-type orbitals. And it's going to go there instead of going to that green spot, because we want to keep them unpaired as much as possible. Okay, that pairing raises the energy. Which means if I hit 7, my electron configuration, if I was to look at a diagram like this, 1, 2, 3, 4, 5, there's 6, there's 7. And that would be a way that we could draw this. That's going to be exceptionally tedious to go through and draw out. So I don't want you to do that. But what I do want you to do is to be able to draw out that configuration. If I'm going to have 7 electrons, I need to label where each of those 7 are. Well, the very first electron was placed in the lowest energy level, 1. It was placed in the S type. The next electron, also in the 1s. We moved to the next electron. Right? We had to move up in energy. So we moved up to the 2nd energy level. First, the S type. Okay? Then we moved up to a new type. Okay? 2nd energy, P type. And then the next one, 2p, 2p. And that would now represent where every single electron was of those 7. So that could work. That is a bit tedious, and so typically what you'll see is a condensed form of that. 1s2, we'd specify the number of electrons in the upper right-hand corner, 2s2 and 2p3. And we now have a way to represent that. 7 electrons, remember, the upper right-hand corner was where we specify the information about the electrons. 2 plus 2 plus 3 hits us with a 7, right? This is really useful so that if I said, say, determine the electron configuration for copper, note it's an entirely different question. Copper, you'd have to go to the periodic table, find the number of electrons, 29, and then you would have to put it together. One of your cheats when looking at a multiple choice would be to sum the number in the upper right-hand corner for your electron configurations for all of your answer choices. That addition is a relatively fast mathematical step, and if it came up to be something other than 29, we know that answer is wrong. That can improve our odds for increasing correct answers on a multiple choice test. Okay, so that could work out for us. We'll look at another cheat for that once we have the periodic table pulled up, okay, which I think we're about to do here. But what I want you to get out of this is that it's where our electrons exist. I would recommend pick anything you want and just start trying to place electrons and come up with what that kind of configuration would look like, okay? That electron configuration would be something like this. There is something known as a shorthand, okay, or the noble shorthand. You are welcome to go through and use that. I'm not testing you on it, so it's up to you if you want to use that. If you move into 151, you'll probably encounter it then. I don't think it's worth the trouble in Chem 130 or our fundamental class. Okay? So we've got a quick review of electron configuration. How does our periodic table come in to help us? Okay, well, if we remember the patterns that I went through and told you to look for, okay, S, we said 2 electrons. P, we said was 6 electrons. D, we said was 10 electrons. If we go through and look at this periodic table, hopefully you start to notice a pattern here. The S had 2 electrons. How many columns are there? Right? Note the red one is all shown with S. The orange one all shown as D. The green one all shown as P. What we're looking at here is that the periodic table is organized according to blocks. And if we kind of section out the table, we really have these kind of blocks that we're assembling. You'll note that the 1s splits and does weird stuff, and that's because it's so low in energy it doesn't quite fit the pattern in both hydrogen and helium. that would be those corresponding elements. Hydrogen and helium carry properties that can allow them to be placed at either cap of the periodic table, and so they're a little bit tricky. So if you kind of ignore them or float them off the table, you can look for these kind of sections. And hopefully what you start to note is that we're seeing this 2, 6, and 10. How many columns are in the red block? Well, there's 2. Why are there 2? Well, because I can only fit 2 electrons in the s-type orbitals. If we take a look at that p section, often known as a p block, there are 1, 2, 3, 4, 5, 6 columns. Why are there 6 columns? Because I can only fit 6 electrons. In the d block, I know we now have to count a little bit crazy, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10. Why 10? Only 10 electrons fit in the d orbitals. Okay? And I said we're going to leave the F off. Now's our opportunity to bring the F back in. If we go through and bring the F in, how many electrons fit in the F orbitals? Okay, well, it's now looking at that block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And depending, I didn't actually count this one out, depending on how your periodic table has decided to sort it, you might encounter seeing 15, and that's because they've taken lanthanum and actinium, or actinium, and included them down there. You're now moving so high in energy that you're getting all sorts of weird discrepancies with electron fill patterns, and that's where it becomes challenging to deal with those. For the sake of a fundamental class, we don't even need to worry about it, so ignore it. Okay? Where you will have to worry about, though, is what's going on pretty much in this upper half. Okay, so you need to be able to describe the fill patterns for everything up there. Officially, and actually I'm gonna kind of undo that, you should be able to do the F section or the S section and the P section for any element in that sequence as well. Okay, but those tend to be a little bit more rare for us looking at, so we can kind of, that was an attempt to faintly erase those. Right? We typically don't dig into those. Again, you move into 151, yeah, you're going to be expected to look at those. But for our fundamental class, we don't need to look at it. Right? So what we need to be able to do is the electron configurations for everything above there. Yes, this is something you can look up on the internet. That takes time. Weigh that time conflict with how you need to go through and evaluate your questions on an exam. Okay, but because the answers are available, you can also test yourself on your ability to come up with these fill patterns. So I did say the periodic table can help us out. Okay, we've got some references. Note the numbers on the left were our energy levels. Okay, if we're going to look at copper, copper is this one right here, okay, that comes in at 29. If I wanted to figure out copper's electron configuration, what I can do is label all 29 electrons. So I could do that quick addition to see if something mismatches. The other thing that I'd recommend to do first would be to find where copper's last electron is located. And what we'll discover in this video is that the highest energy electrons are typically the most relevant for us. Okay, so what can I do? Well, I can look at the section, the energy level that copper is located in. And so if we go to the extreme left, we'll note that it's in energy level 4. The d orbitals, however, are offset by 1. And that's where things can get confusing, as people go, well, the pattern doesn't hold. Why on earth would we have moved the d orbitals down out of that pattern? Well, we moved it out of the pattern to account for the weird fill pattern that we get, that we fill 4s first, okay, instead of filling d. Okay, the analogy that I'll use here in a second isn't perfect, but it works really well to describe a lot of physical observations that we encounter, and it does show up in other more advanced systems. So let's go through and kind of build this out. For sure, this whole third energy level is going to get filled. Okay, so I would need to account for all of those. I would start with my one energy level, which has the S type, 2 electrons, second energy level, and so what I'm doing is moving through here. Second energy level, S type, I'm filling both of them up. Second energy level, P type, I'm filling all of them up. Third energy level, S type, all of them up. P type, all of them up. Okay, and now what's the next thing I would move to? Because remember, we read left to right, top to bottom. Well, the next thing I would encounter would be right there where all that confluence of arrows is going. Okay, that is the fourth energy level. Okay, it is also starting in the S block. And I fill all of that up first. Okay, then I move to the third, or I move to the D block, and the D block has been offset by 1. So it comes in as a 3D, whereas copper in that, it's in the 9th column. So we can look at that number as, whoops, if I learned how to spell column right, is a column reference for your electrons, and that's useful. If you go back and look at all the other numbers, those kind of grid line out, it's a game of Battleship, where you're supposed to be referencing. Right? And so that's kind of handy from the periodic table point of view. Okay? I did say that there's a little bit of a pattern that we could look at here. Why would I have done 4s2, 3d9, and not the other way around? Why not have done the 3d first, 3d10, and then 4s1? Well, a lot of this, as far as fill patterns go, has to do with symmetry behind how we filled these orbitals. Right? If we move for our very next electron after the 3p6, should we be going to 4s or 3d? Right? If we go to 4s, we get the pattern that we would see. We would get a 4s orbital with 1 electron in it. If we went to the 3d, well, the d have 5 orientations. If I put 1 electron in there, I'd have that system. Okay? And this may seem a little bit odd, but if we go through and compare these two cases, so case 1 and case 2, case 1 ends up being prettier. Why is it prettier? 1 orbital with 1 electron in it. It's symmetric. Case 2, we have 5 orbitals with only 1 electron. That's not symmetric. You've got 4 orbitals that are unoccupied and only 1 that has 1 electron. Right? That symmetry argument does play into reactions much, much later in chemistry that you probably won't ever encounter unless you're planning on becoming a chemist. And you'll probably learn it much better than I can teach it. Right? But that symmetry argument helps to explain why we fill 4s before we fill 3d. It's a case of Beauty and the Beast. Okay? I would rather be symmetric than asymmetric. And for those of you being like, well, that's totally not true, there's a reason people go to become plastic surgeons. There's a crap ton of money in it because people will pay to become beautiful. Okay? That symmetry argument plays just as much for chemistry as it does for people in the real world. Okay? So what we've got is our periodic table that summarizes out these individual blocks. It helps us to identify our electron configurations, and we can kind of move through it. When I first learned chemistry, this was one of the first things that popped up, and I thought it was the coolest thing ever. Okay? You would outline out this grid pattern, and then you would just kind of move through. Whoops, that's an eraser. You would move through it, say, well, my electron configuration would be 1s first, double back, 2s, double back, 2p, 3s, and so on. 3p, 4s, note the discrepancy there. 3D, and you continue on and on and on and on, right? This doesn't explain why we're getting that mismatch, and that mismatch, right, has to do with the energy levels getting closer and closer and closer. So we start to see the fill patterns change, right? The other problem with this that I found as soon as I moved to an exam, I could not draw this out, right? Whoops, not a big deal. For this thing to work, you have to be able to draw like graph paper, right? And if you can't draw like clean graph paper, then this method is useless, right? In which case it makes more sense to be able to interpret the periodic table, right? But ultimately what you're trying to do is get to an electron configuration. So we're going to pick an element that's near and dear to me. Let's take a look at carbon. And if we go through and look at carbon, carbon has 6 valence electrons. Okay. And if we were to go through and place those out, we'd start with the 1s. We're going to fully fill the s orbital, which holds at most 2 electrons. We'd then move to the second energy level, which is going to be our 2s with 2 electrons. And then we'll move to 2p, again with 2 electrons. Why 2 and not 6? Remember, carbon can only hold 6 total electrons. 2, 4, 6 were there. Right? Chemical properties. If I'm now going to bring 2 atoms near each other so that they interact to do something cool or crazy, I need to have those electron clouds interact with each other first. The most likely electrons to interact are going to be the highest energy electrons, so the last ones that we filled up. Right? But remember, highest energy electrons. When we're looking at this last symbol, where is the energy level dictated? Energy level was that number in front, that 2. Well, doesn't that also show up in the previous one? It does. Okay? So when we're talking about valence electrons, we're talking about the highest energy electrons. And those highest energy level electrons are going to be anything with the largest number in front of them. So in this case, the valence electrons for carbon are going to be whatever electrons are in the orbitals that have the 2 in front, which means we're going to get 4 valence electrons. Right? If we were to switch this up and try it on a different element, let's say silicon. Okay, silicon has vastly more electrons, so we might predict more valence electrons. So let's stick with 14 electrons. If we were to go through this fill pattern, we've got the fill pattern listed out for us, so we don't even have to use the periodic table. We can just move through that. 1s2, 2s2, 2p6, 3s2, 3p2. 2, 4 with that 6 gets me 10, plus another 2 there and 2 there, 14. I've got my 14 electrons. Okay, so cool. How many valence electrons? Well, the highest energy level would be 3. How many electrons do I have total in my valence? I have 4. I have the exact same number of electrons as I have carbon. Another interesting pattern on our periodic table, if you go ahead and take a look at the Roman numeral at the top of the column where carbon and silicon are found, you'll find it's 4. For the main group elements, that would be the S block and the P block, the Roman numeral tells you the valence electrons for an individual atom. The whole point of electron configurations is ultimately to be able to get you to this valence electrons, and it turns out that all we have to be able to do is interpret the periodic table, and the periodic table tells us those valence electrons. We don't have to dig into the electron configurations. So that's kind of neat. So practice finding your valence electrons, recognize where they're found on the periodic table, and recognize where they're found in the electron configurations, because I can already foresee a theoretical exam question where I give you an electron configuration and say how many valence electrons. So you wouldn't be able to use the periodic table, you'd have to pull it from the question itself. Okay? Come on, work with me here. So Back to our atomic radii. If we looked at our atomic radii, we saw that there were two trends. We had a column trend, okay? It got bigger down the column. Notice it's bigger. And then we also noted that it got bigger left to right, okay? And that's in our row. And for those of you wondering, yes, I have problems with left and right. That would actually be right to left. Okay, it got bigger. Down the column, the explanation kind of made sense because we have more electrons, and that was the argument that we'd used before. Okay, but if we use the more electron argument, then we would expect that same argument to hold for the row, more electrons. But when we move right to left, we actually have less electrons. So that theory doesn't work, okay, or that explanation doesn't work. And this is where we have to use our understanding of where our electrons exist. The electrons exist in orbitals, okay, of particular energy levels. So when we move down a column, it gets bigger because the electrons are going to a higher energy level. Right? That makes it go further away. Well, what happens when we move across the row? When we move across the row, same energy level. Well, if it's the same energy level, it shouldn't change the size, right? This is where we also have to consider something else. There's an and here. If they're going in at the same energy level, we don't expect a change in the size of the atom. But we also have to remember that when we move left or from right to left, we're also changing the nucleus. When we move down a column, it didn't matter because we're jumping in energies. That was a big difference. When we move through a row, we aren't changing the energy levels, which means other things can come in and contribute. That other thing that comes in and contributes has to do with the nucleus. When we move right to left, we have less positive. Okay, why do we have less positive in the nucleus? We have less protons. If there's less protons, there's less of that attraction between the positive and the negative, which means the electrons can float out just a little bit further than they could if there were more protons there. Okay? So when we're looking at atomic radius, we do have to be careful in our explanations. It's not just more electrons. That is a bogus explanation. Anybody telling you that is wrong. Okay? When we're moving down a column, we're going into higher energy levels. We have to understand that we're changing the energy level of our electrons. When we're moving through the row, it's two things. Number one, they're at the same energy level. Okay, which means the electrons don't change the distance from the nucleus. Our radius stays constant. But when we add to that, the nucleus also has less protons from right to left. Okay? That means the electrons don't get held as tightly and they can spread out just a little bit more. Okay? So those are the two pieces that you have to be acknowledging when going through and looking at atomic radius. If you were asked to explain. If you're not asked to explain, you just have to have the answer memorized, and that's where having a trend drawn out, like I have with the arrows on our periodic table, pretty slick. Okay. The next thing we could go through and do to look at other trends, we can reference ionization energy. Ionization energy has a couple different concepts tied in with it. First and foremost, you need to know what it means. Okay. It is the energy to remove an electron. Okay? And officially in the gaseous state. What charge would our atom be if I removed an electron? If we lose a negative, that means we're positive. So ionization energy is literally talking about the formation of positive atoms. Which atom? Any and all atoms. Ionization energy specifically says we're making positive atoms. Doesn't matter what atom it is. Okay? There are trends associated with this. As you might imagine, these trends are similar to our atomic radius. Radius is where those electrons were located. If ionization is talking about the removal of electrons, if we think back to our depiction of our orbits, our energy levels, these moved up in energy, right? So if I have an electron located down in the first energy level versus an electron located in the third, to remove the electron, I'm talking about that gap in energy. Or I'm talking about that gap in energy. The larger the jump, the more energy required. So if we think about atomic radius, right, the larger the radius, the smaller the ionization energy. Right? And this holds true for the vast majority of cases that you will encounter. Right? And what we're looking at in those explanations is roughly the same thing that we saw with radius. Electrons in our lower energy level, it's going to require more energy to rip it off. Right? If it's in across a row, while in the same energy, it's still pulled closer, so it's going to require more energy to rip it off. Right? So what we can look at within this is a couple weird things. Number one, it says in general. And in general, you should always freak out because in general means not always. There are exceptions to this. Right? This table takes a little bit to get used to, so I'm going to walk through it real quickly. Each of these dots represents an element, so that would be hydrogen. The next element I would encounter would be helium, so I'm moving up. So all we're doing is adding one atomic number, so we're adding a proton as we move through. Then we move to lithium, and it goes up all the way through neon. And so each of those dots is the existence of a new atom, right? And if we take a look at the large trend, right? Hydrogen, neon, argon, krypton, xenon, radon. Here they are right here. Within a column, what happens? Well, the ionization energy decreases as we move down the column. Why? Larger atom, easier to remove that outermost electron. So hydrogen we would expect, or helium we would expect to be very high energy. When we look across a row, hydrogen and helium, I know hydrogen's not on that list, we would expect hydrogen to be lower in energy than helium because helium was a smaller nucleus. So helium's going to require more energy. So the trends all fit on here and work out pretty well, right? It isn't perfect, right? And so what I want to draw your attention to are these little hiccups, okay? These hiccups are what would be referred to by most people as exceptions, okay? They aren't really exceptions. What they are is an incomplete description of the pattern that we're seeing, okay? We need to dig into what's happening at those points to read or to resolve our theory on ionization trends, right? Those trends aren't perfect. To really understand this, you have to be looking at our electron configurations for each and every single atom and use our general understanding. How much energy is it going to take to rip it away, right? If we go through and do that, that helps to explain what's going on here. I really enjoy that discussion about that exception between, say, if we looked at oxygen and nitrogen, okay? The problem is it's kind of outside the scope of a Chem 130 class. It might be something I throw at you as an extra credit question. It's probably something that if you're interested in chemistry, you talk to me about it. I have already given you the fundamentals to be able to have this discussion and figure out why we would expect that mismatch. Okay, why? Not easy, but you can do it, right? Real quickly, just to kind of give you a general idea on that pattern, right? If we looked at oxygen, 1s2, 2s2, 2p4, that would be oxygen. If I ionize this, this becomes 1s2, 2s2, 2p3, and that would be oxygen plus, okay? That's what we're discussing. To make an extra huge big hint to kind of help with this, the last thing that you should really be doing when you evaluate this is recognize that I don't care about the core electrons, I really care about the outermost. So I'm talking about the 2p electrons. I had 1, 2, 3 2p orbitals. I have 1, 2, 3 2p orbitals. When I look at oxygen as an atom on its own, we said it was 2p4. It looks something along those lines. Oxygen, after it's ionized, 2p3, looks something like that. Okay? Again, Beauty and the Beast. It's awesome. I think it's cool, but I'm going to leave it at that. Okay. Last, or almost last thing that we'll look at in this video, electron affinity. It's not officially in our textbook. Okay, it's only really here in the slides. Don't worry about the trends. The big deal here is this is the energy released to grab an electron from the vacuum. So it's the reverse of ionization energy. So what I want you to kind of recognize here is that we are taking electrons from the vacuum and I'm pulling them in. Right? That's going to release energy because the electrons are in the vacuum are high energy. When they're associated with me, they're more stable. Right? So these are going to be energy releasing reactions. What charge would I become if I accepted an electron? Yeah, I'd become negative because I'm increasing the number of electrons. That's the big thing I want you to get with electron affinity, is recognizing that charge differential. Right? Why mention both of these things? Well, the point of mentioning both of these things is this gets us to the concept of electronegativity. And electronegativity is incredibly important because that helps to explain what's happening within bonds, which is our very next section or our very next unit. Okay, and Pauling was the one that came up with a way to kind of relate or determine electronegativity, and ultimately it's coming down to the ability of an atom to take bonding electrons from another atom. So this is a blend of ionization energy and electron affinity, though officially not either of them, because in both ionization and electron affinity, there's only one atom. In electronegativity, there's two atoms. You're looking at how those two atoms interact with each other. Right? This is an incredibly important trend to have memorized. It helps dictate nearly all of the intermolecular forces that we'll talk about at the very end of the semester. It helps us to identify what kind of bond types we've got, which is important for both nomenclature and for Lewis structure. Right? So knowing your rough electronegativity trends is helpful. That trend, fluorine is the most, and cesium is the least. So fluorine, most, and then cesium, least. You might ask, why not anything down there? Those are so reactive as materials that we haven't determined their electronegativities, right? The noble gases, you'll also notice, are flatlined. They're so unreactive that they don't react, so we can't predict or rank their electronegativities, okay? And it's the interplay between those that really dictates the bonding patterns that we'll see and predict in the coming unit, which makes me nervous. Yeah, and that's going to be chapter 12, our types of bonds. Okay, so we'll look at that in a little bit. And with that, thanks for watching. And the other button, computer.